Welcome to Quantum. In this video, we go through a lightning introduction to nuclear physics, not by theory alone, but through carefully designed multiple-choice questions that reveal the structure of the subject. The goal is simple: understand the physics behind each statement, not just memorize answers. Rutherford scattering reveals the nuclear atom. The force is not short-ranged. It is a Coulomb force. Because of this, the alpha particle follows a hyperbolic trajectory. Most alpha particles pass almost straight through the atom, but a few are scattered through very large angles. This means that the positive charge cannot be spread throughout the atom. It must be concentrated in a very small, compact nucleus. The Rutherford cross-section is proportional to 1 over sine to the fourth of theta over 2. It becomes very large at small angles. It also depends on the charges of the projectile and the target. Finally, the impact parameter controls the scattering angle. A large impact parameter gives a small deflection. A small impact parameter gives a large deflection. So Rutherford scattering teaches us that the atom is mostly empty space with a tiny, dense, positively charged nucleus. The nuclear radius grows like A to the 1/3. This means that the nuclear volume is proportional to A, so the density of nuclear matter is approximately constant. This is a sign of saturation of the strong force. Each nucleon interacts mainly with nearby nucleons, not with the whole nucleus. Electron scattering is used to measure nuclear size because electrons interact electromagnetically. They probe the charge distribution of the nucleus. The standard value is R0, approximately 1.2 femtometers. Although nuclei have a surface thickness, the density falls off gradually only near the boundary. So, the sharp radius is an approximation, but a very useful one. The orbital magnetic moment comes from a circulating charge. Its sign depends on the charge, and it is proportional to angular momentum with a factor q over 2m. From minimal coupling, momentum becomes p minus qa. The term linear in A gives the magnetic interaction, while the A squared term is usually negligible. For a constant magnetic field, a convenient choice of vector potential simplifies the Hamiltonian and reproduces the correct magnetic field. Now, nucleons show something deeper. The neutron has a magnetic moment, even though it has no charge. This tells us that nucleons have internal charged structure. Inside nuclei, pairing is essential. Even nuclei typically have zero spin. Unpaired nucleons dominate the total spin and magnetic moment. The semi-empirical mass formula describes the nucleus as a liquid drop. The volume term scales with the number of nucleons. It reflects the saturation of the strong force. If every nucleon interacted with all others, the energy would scale like A squared. But it does not. It scales linearly with A. Surface effects reduce the binding energy. Nucleons at the surface have fewer neighbors. This leads to a correction that scales with the surface area. The Coulomb term also reduces binding. Protons repel each other, and this effect grows with charge. The symmetry term comes from quantum mechanics. It reflects the Pauli principle. If neutrons and protons are not balanced, the energy increases. The pairing term adds extra structure. Even nuclei are more stable. Odd nuclei are less stable. Now, from a microscopic point of view, we use the Fermi gas model. Nucleons fill momentum states up to a maximum value. This is the Fermi momentum. Density determines this scale. Higher density means higher Fermi momentum. The average kinetic energy is smaller than the Fermi energy. It is proportional to it. If neutrons and protons are not equal, their Fermi levels separate. This naturally produces the symmetry energy. Finite size effects introduce surface corrections. These corrections reduce the number of available states. Finally, the balance between volume, surface, and Coulomb terms explains a key fact. Binding energy per nucleon reaches a maximum near iron. This is why neither very light nor very heavy nuclei are the most stable. Alpha decay is one of the clearest examples of quantum tunneling. We treat the alpha particle as a preformed cluster inside the nucleus. The coordinate r measures the distance between the alpha particle and the daughter nucleus. Outside the nucleus, the Coulomb repulsion dominates. Classically, The alpha particle cannot escape if its energy is below the barrier. Quantum mechanically, it can tunnel through. The WKB exponent measures the difficulty of this tunneling process. A higher Coulomb charge makes tunneling harder. A larger decay energy makes tunneling easier. The outer turning point is where the Coulomb potential equals the decay energy. The decay constant has two parts. First, the assault frequency, how often the alpha particle hits the barrier. Second, the tunneling probability. This gives lambda equal to n times p. The Geiger-Nuttall law then follows naturally. The lifetime decreases rapidly when the decay energy increases. So alpha decay is not only nuclear physics, it is quantum mechanics made visible.